Hello and welcome back. In this video, I'm going to give the solution for problem M, Candies from Atcoder Educational DP Contest. The problem states that there are n children numbered from 1 to n, and they have decided to share k candies among themselves such that for each I between 1 and n, the ith child must receive the number of candies between 0 and a of I. So this is a parameter for each child which is given to us, inclusive in this range, and also no candy should be left over. So we want to distribute the candies, all of the k candies, among the n childrens such that all of them are distributed with the condition that is each child receives candies between 0 and AFI, and we need to find the number of ways to share such candies modulo the value 10 to 9 plus 7. And here two ways are said to be different when there exists a child who receives a different number of candies. Let's also look at the constraints. N is up to 100 and k is up to about 10 to 5, and the number of candies that the ith child can receive is bounded by k, obviously, because we only have k candies left to distribute. So let's try to look at the problem statement in terms of mathematical representation. So we are given values which are the ranges for which each of the ith child can take the candies up to, right? Now we need to distribute n candies among themselves. So let's say d1 is the number of candies received by the first child, d2 by the second, d3 by the third, and so on up to n. And we know that di is in the range 0 to afi, because the ith child can receive only up to the values of number of candies in this range, and this total should be exactly k. So this is what the question asks, that all the candies should be distributed. So this is the first condition that we need to consider, and the second one is that the sum of the values of all the distributed candies should be exactly equals to k. These are the two conditions that we need to meet, and essentially the number of ways to distribute the candies is same as the number of possible arrays, number of possible sequences d that are possible. Possible number of sequences d with the constraints by following the conditions 1 and 2. So we can solve this recursively. We can iterate over the number of candies that we can give for each child. So essentially the first child can be given candies in this range. So if he is been given, let's say, d1 number of candies, then the number of candies that are left for this one will be k minus d1. And if this child is again given d2 number of candies, then the number of candies left with us is k minus d1 minus d2. Since this is the main idea, to give candies from one, basically distribute the candies from left to right for each index of the ith child, and we also need to keep track of this variable. So we also need to know how many candies that we have left. Essentially we started with k, we had k number of candies left with us, and by distributing one after the other, it got reduced by the amount that we gave to the previous children. So this was changed. So it is important to store this parameter in the state of the recursion. So this parameter goes in the state of the recursion, and we also need to know what are the ID of the child that we are currently giving the candies to. So this is the two important parameters. First one is the state, and the second one is the number of candies that we have left. And essentially we also need to iterate over the number of candies that we can distribute to the ith child. And this will be a for loop from range 0 to a of I, but may have only this many number of candies left. So this will be essentially loop between minimum of this two. This will be iterated over the transitions of the recursion. This will be the transitions from distributing, let's say, the ID number of candies to the ith child, and let's say the left was this amount. Then for the ID plus 1th child, the left would be left minus the candies that were distributed to the previous one, and again this will also be given some again number of candies, and this will go on one after the other. Essentially we will arrive at a base case where index is n plus 1, which is the size of the array, and here we need to check whether we are left with no candies. And we see essentially the index previous to this would be index n, and we would have given these n distributed candies among n children. So our construction is complete at this stage, and arriving at this base condition means that we have found out one way to distribute the candies, and whenever left is 1, it means that we have found out one way and we can return 1 from this case. This is the main idea. Let's go over the implementation for this. So n and k are the inputs. A is the array which is given in the input. We are starting at index id equals to 1, and we have key candies left, hence these two parameters of the recursion. The number of candies left for the id child is represented by the variable rem, and we need to check whether rem is always positive or 0. If it is not, then that means that we have distributed more number of candies than that were available to us. And if we arrive at a base case, which means that we have found out one way to distribute the candies, hence this condition will be evaluated to 1 whenever we have distributed all of the key candies, exactly key candies. This is the memorization part, and this is the first choice to either don't give any number of candies to the ith child, so we can choose not to give anything to this, so we can give 0, or the second is this for loop, give positive number of candies, which is from 0 to a of I, a of id, as the convention follows. And for each of them we need to count out the number of ways which will be added by taking the values from the next state and taking the mod alongside it. And if we are giving, let's say this variable denotes the number of candies that we are giving for the id child, then the number of candies that will be left for the next child would be the amount of candies that we already had minus that we used up, and finding out the total number of ways and returning the answer from here. This will be the time complexity for this would be n values for id, key, order key, values for number of events, the second state, and this for loop is again order key, because order a of I is bounded by order key. Hence in total this will be order n key square time complexity solution, which is not acceptable because the constraints are very large and we need to find out a better solution for this. Let's try to convert this recursive into iterative solution. The same approach that we have used in the recursion, we are going to convert it into bottom-up solution. So inputting n key and the array A using this state dp, and here I am using memory optimized solution. So let me also explain that. So if you saw earlier, we had two states in the dp as well as the table in which we are memorizing the answers, but in the iterative solution we only have one state because the id state only depends on id plus one state, right? So the dp table looks like this for the iterative solution. So whenever we are finding out the values in the id row of the dp, we are referencing only the id minus 1th row from the entire dp table, memorization table. So we are only referencing the values for the yellow region from the red one. Hence all the values before that are not relevant. Hence we can use two dps for this, previous and next one. This is how memory optimization dp works. Let's try to look at the solution for this. So this is the base case. We have one way for every possible way to distribute these many number of candies between the for the child with index 0, and for each of them from left to right we are going to update the answer, and the next dp value, which is basically we have computed the dp values for index 0, and now we will compute the dp values for index 1. These values are stored in dp and these next values will be stored in ndp. So this will be updated from the previous computed dp values. So this is the variable of column total, the number of total number of candies that the ith child can receive, and we are going to give it some number of candies in the permissible range, and this is only possible when we have that many number of candies left. This is condition for that, and this is updated by taking the same recursive function that we saw here. So total was this value that was remaining, and this was the amount that we gave the ith child. This is translated in the same manner in this form, and again the dp for the next case would be updated by swapping these two for the next iteration. So now this becomes the dp, and the next would be computed from here, and this is how the entire workflow will look like. And in the end, the number of ways to distribute all the key candies will be stored in the kth index of the dp array. So this is the iterative version. Again, time complexity will be order nk square, because this loop goes for order n time, this one for order k, and this is again bounded by order k. Hence in total this would be order nk square time complexity. Now let's try to optimize this. If you notice that to update the value for the next TP, right? Let me clear this once. To update the value at a particular index for the next TP, we add the values in this range. So let's try to figure out what this range is actually. So say give is 0. In that case, this would be TP of total minus 0. This would be added in this variable. So we need to know what all values are getting added in this during the transitions. When it is 1, this is the value that is added. When it is 2, this one, and so on, until the maximum value that give can take is e of I, right? So this is what e. So instead of iterating over all the possible values and going over all these ranges, we can find out this sum. This sum is a consecutive subarray of the previous TP. So this was the previous TP values, and let's say index total is somewhere here, right? And total minus e of I is somewhere here. Hence we need to know what is the sum in this range. This is the LNR for the subarray, and this is already known for the ith iteration. This is already computed. So we can build prefix sums over this subarray, over this array. And compute the sum from, let's say, dp any L to R in order 1 time complexity. Hence the innermost for loop can be eliminated. So this for loop can be computed in order 1 time. This will give us a time complexity of order n times k. This is the main idea. Now let's go over the implementation. This is the range of indexes that we are interested in to update the value for the any index in the next TP. Okay, so as I mentioned here, initially it would be total minus 0, then total minus 1, then 2, and so on, until it is total minus e of I, which is the maximum value that give can take. It started with this one and ended with this. So this is the main idea, and this are the LNR for the ranges for which we need to find out the values of dp, and this is the function that is going to handle that. If dp is already a prefix sum subarray, then sum of dp in this range, or let's say prefix dp, is this array. Let's not confuse the values that we are going to sum up. Values in this range can be computed by taking the sum of the first r values and subtracting the sum of the first L minus 1 values. This will be done in order 1 time complexity. And to construct this, we will require order 3 time. Okay, so as we saw, this is the initial dp array, and we are going to compute the prefix sums over it. in place. This is computed in order k time, and we are doing it in place. We are not using a separate array, which I mentioned here. So finding out the sum of dp values in a particular range, which is given by this function, takes inputs L and R and simply returns the value dp of R minus dp of L minus 1. Plain and simple as that. We replaced this order k for loop with order 1 time complexity with order k pre-computation. Right. So let me also give you an overview. So initially we had this dp array, and we need to update the next dp array, which this denoted the dp values for index id, and the next one would denote the dp values for index id plus 1. Now updating any index in the next one, and dp of k required order k time complexity because it took the sum of elements in a particular range in the previous one, right? So updating any n dp of k, which was some index k in the n dp array, required iterating over a particular range in the previous array, the previous dp array, right? This was dp. So to compute this, we went over this range, sum up the values in this range, and updated the values at a particular index this. But this was already known, this was already computed, and we tried to update the values for the next dp. Hence we computed a prefix sum over this array. So updating this in dp with the sum of values in the range, it was total minus a of I, or in this case it would be kth index, so k minus a of I to, I guess it would be k minus 0, which is k. At k would be done in order n time, order k time with the initial solution, and with prefix sum we can find out this value in order 1 time. Hence this updation would take order 1 time complexity, and the overall solution would be order n times k. And memory wise, it would only take order k memory because we are only initializing the arrays of size k. dp only has stores the values for indexes 0 to k, and the input array will also be considered. So this is the time and memory. That's it about this video. Do let me know if you have any doubts or suggestions regarding this. Thank you.